Black hole, dark matter, the Big Bang. These concepts seem vast, beyond our understanding. But in reality, the laws that govern the cosmos emerge from the microscopic world of quantum mechanics. Here, matter can exist and not exist at the same time. Particles influence each other instantly, and space-time itself might be nothing more than a projection of information. Today, we're diving into the strangest and most mysterious realm of science, where quantum laws shape the universe, where our reality might be just one of many, where space and time could be nothing but an illusion. Are you ready? Then let's begin. Black holes are cosmic monsters. They devour stars, bend light, and warp space-time itself. But what happens deep inside, beyond the event horizon? According to Einstein's general relativity, gravity becomes infinitely strong at the center of a black hole, collapsing everything into a singularity, a point of infinite density where the laws of physics break down. But infinities don't exist in nature. They signal a flaw in our understanding, and that's where quantum mechanics steps in. Unlike classical physics, quantum mechanics doesn't allow for infinite values. Instead, it suggests that at the heart of a black hole, gravity itself must behave quantum mechanically. This is what scientists call quantum gravity, a theory that combines Einstein's relativity with the bizarre rules of quantum mechanics. But here's the problem. We don't have a working quantum theory of gravity yet. However, some models suggest that black holes might not have singularities at all. Instead, space-time could undergo a quantum transformation, leading to something unexpected, like a Planck star, a remnant that eventually explodes, releasing everything it swallowed. But what if this idea applies not just to black holes, but to the entire universe? Before the Big Bang, there was nothing. No space, no time, just pure quantum uncertainty. But in the quantum world, even nothing is unstable. Particles constantly pop in and out of existence due to quantum fluctuations, tiny random energy shifts that happen everywhere, all the time. And some physicists believe that one such fluctuation triggered the birth of our universe. Think of it like a cosmic bubble forming out of the vacuum. In an instant, it expanded, faster than the speed of light, in what we now call cosmic inflation. In mere fractions of a second, the entire observable universe emerged from an incredibly tiny quantum fluctuation. But here's where it gets even stranger. If quantum fluctuations created our universe, could they also be creating others? The theory of eternal inflation suggests that new universes are constantly being born in an ever-expanding multiverse, each one with its own physical laws, its own reality, which raises a mind-blowing question. Could the mysteries of our own universe, like dark matter, be explained by something outside our universe? If our universe was born from a quantum fluctuation, what else could emerge from the quantum world? Some scientists believe that the answer to one of the greatest cosmic mysteries, dark matter, might be hidden within the strange phenomenon of quantum entanglement. In the quantum realm, particles can become entangled, meaning their states are instantly connected, no matter how far apart they are. Change one, and the other changes instantly, even if they're light years away. This connection happens with no physical link, defying our classical understanding of space. Einstein called this spooky action at a distance because it seemed impossible. Yet time and time again, experiments have confirmed that entanglement is real. We still don't fully understand how or why it happens, only that it does. But what if entanglement isn't just a strange quantum trick? What if it's actually shaping the structure of the cosmos itself? Some physicists propose that dark matter, the invisible, undetectable substance making up most of the universe, might not be made of unknown particles at all. Instead, it could be a network of quantum entanglement stretching across the universe. Imagine every star, every galaxy, connected not by gravity alone, but by invisible quantum threads, a hidden framework holding everything together. Instead of missing mass, dark matter could be an effect of these entangled fields, influencing galaxies in ways we have yet to understand. If this is true, then dark matter isn't something we can find. It's not something we can touch. It's a fundamental property of space itself, a quantum effect on a cosmic scale. And if entanglement can hold galaxies together, could it also explain what happens when information falls into a black hole? For decades, physicists believed that anything crossing the event horizon of a black hole was lost forever, that black holes erase information, violating one of the most fundamental rules of physics. According to Einstein's theory, a black hole is a one-way door. Matter and energy fall in, but nothing, not even light, can escape. Anything that crosses the event horizon is gone from our universe forever. But quantum mechanics tells a different story. It suggests that information can't be destroyed. It must be preserved in some form. And this creates a paradox. So where does the lost information go? One possibility is that it's not lost at all. Instead, information may be encoded on the surface of the event horizon itself, like a cosmic hard drive, storing everything that has ever fallen in. When a black hole eventually evaporates through Hawking radiation, the information might slowly leak back into the universe, piece by piece. But some physicists take this idea even further. They propose that black holes don't destroy information because black holes don't actually exist the way we think they do. What if, instead of a singularity, the core of a black hole is something else entirely? Something that preserves information in a way we don't yet understand? Some theories suggest that black holes might be holograms, projections of deeper quantum processes. Others propose that they could be quantum tunnels, gateways to other parts of the universe, or even to parallel realities. If black holes don't truly destroy information, what does that tell us about the nature of reality itself? Some physicists believe the answer lies in one of the most mind-bending ideas in modern science, the holographic universe. Imagine that everything you see, touch, and experience, every planet, star, and galaxy, isn't truly three-dimensional. Instead, it might be a projection from a deeper, two-dimensional layer of reality. This idea comes from an unexpected place: black holes. If information is encoded on a black hole's event horizon, then maybe our universe works the same way. What if everything we experience, space, time, even our own consciousness, is just a higher dimensional illusion, projected from a deeper quantum structure? It sounds like science fiction, but mathematical models support it. The physics of a black hole can be fully described by the information on its surface, without needing to account for what's inside. In the same way, our entire universe might be describable by a distant cosmic boundary, where the fundamental laws of physics are written in quantum code. But if the fabric of reality is built on quantum information, could we manipulate it? Could we one day teleport across space, not as science fiction, but as science fact? We already know that quantum teleportation is real. Scientists have successfully transferred information between entangled particles across distances. Not physical matter, just the quantum state of a particle instantly appearing somewhere else. But what if we could scale this up? What if quantum teleportation wasn't just for subatomic particles, but for entire atoms, or even living beings? Teleportation, as we imagine it, stepping into a machine and instantly reappearing elsewhere, would require transferring all of the quantum information in a person down to the last atom. It's an unimaginable challenge, but theoretically possible. If entanglement can link distant particles, and if quantum information can be transferred without delay, could this be the key to interstellar travel? In a universe where space-time itself may be an illusion, does distance even matter? Some physicists speculate that wormholes, hypothetical bridges between distant points in space, might actually be quantum entanglement on a cosmic scale. If true, this would mean teleportation isn't just a dream. It could be the foundation of the universe itself. But before we start teleporting across galaxies, there's an even bigger question. If quantum mechanics allows for infinite possibilities, how many universes are actually out there? If teleportation is possible, if space and time themselves are just quantum phenomena, then we have to ask, is our universe truly unique? In the quantum world, particles don't exist in just one state. Until observed, they remain in a superposition, existing in multiple states at once. But when we measure them, they choose a single reality. But what if that choice isn't random? What if every possible outcome happens in a different universe? This is the many worlds interpretation, one of the most radical ideas in quantum physics. It suggests that every quantum event splits reality into countless parallel universes. Every decision, every possibility, every tiny fluctuation at the quantum level creates a new branch of existence. Right now in another universe, a version of you made a different choice, and in another, an entirely different version of the cosmos unfolded. It's not just a wild theory. Some physicists believe this is the best explanation of quantum mechanics. If true, it means reality isn't a single timeline. It's an infinite, ever-expanding web of parallel worlds. But if infinite universes exist, what does that mean for space and time themselves? We think of space and time as fundamental, the stage where reality plays out. But what if they are illusions? Some physicists propose that space-time isn't a fixed, unchanging backdrop. Instead, it might be an emergent phenomenon, something that arises from deeper quantum rules. Think of temperature. It doesn't exist at the level of individual atoms. It's an emergent property of many particles interacting together. What if space and time work the same way? Quantum mechanics suggests that space-time isn't smooth. It's made of tiny, discrete units, like pixels on a screen. At the smallest scales, reality dissolves into a chaotic quantum foam where distances and durations have no fixed meaning. If this is true, then time itself may not be what we think. It may not flow in one direction, it may not flow at all. And if space-time is an illusion, then what is reality really made of? Perhaps the universe isn't a vast expanse of empty space, but a structure of pure quantum information. If that's true, then the future of space exploration won't be about traveling through space at all. It will be about unlocking the deeper, hidden laws of the quantum universe itself. If space-time is just an illusion, if reality itself is built on quantum information, then what does this mean for the future of space exploration? For centuries, we imagined traveling the stars as a problem of engineering, building faster rockets, finding new energy sources, pushing the limits of technology. But what if the real breakthrough isn't about propulsion at all? What if the key to exploring the universe lies in manipulating reality itself? If quantum mechanics governs the cosmos, then the future of space travel may not be about moving through space, but about bending space to our will. Quantum teleportation, wormholes, even harnessing the structure of space-time itself. These might not just be ideas for science fiction. They could be the foundation of a new era of exploration. Imagine a future where we don't launch ships to other planets. We simply step through quantum doorways that connect distant worlds instantly. A future where we don't just observe black holes. We extract energy from them, using the power of quantum fields to fuel entire civilizations. A future where we don't just search for alien life, we find it in parallel universes, reaching across the multiverse itself. But if quantum physics has taught us anything, it's that the deeper we look, the stranger the universe becomes. Because in the end, the greatest mystery isn't just black holes, or dark matter, or the fabric of space-time. The greatest mystery is reality itself. What is the universe really made of? Are we just observers, or are we part of the quantum code that shapes existence? And if space, time, and even our own consciousness are all quantum phenomena, then the biggest question remains: who or what is truly observing us?